competency level assessment to become a journeyman and tools for control system analysis, I will be discussing generalized solutions to second-order systems. There are two kinds of second-order systems that we have discussed so far, and they are unforced and unforced. They are unforced and forced. And as you can see from my two equations, this is the unforced second-order system, and this is the forced second-order system. And one of the main differences between them is that the unforced is set equal to 0, and the forced is set equal to an actual value. And this is because an unforced system does not have any force acting on it, so therefore it's in equilibrium, so it's set equal to 0. But a forced second-order system does have something acting on it, so we do have a force that we have to set it all equal to. So I will be discussing the solution to the unforced system first. And the equation is 4y double dot plus 8y double dot, or 8y dot plus 4y equals 0. And when t equals 0, y equals 0. And when t equals 0, y dot equals 3. So the first thing that we can do with this unforced equation here is simplify it. So we can divide it by 4. And this is going to leave us with y double dot plus 2y dot plus y equals 0. And then now we're trying to find some constant variables in this equation to actually solve for the dampening coefficient. Because the dampening coefficient in this situation will tell us what equation we need to use. So we can find omega n squared from this equation, which is actually going to be the one that attributes to this y right here, which means that omega n equals 1. And then we can also do the same thing to find the dampening coefficient using our omega n. So 2 times the dampening coefficient times omega n equals 2. And that is from our 2 right here accompanied with the y dot. And then 2 dampening coefficient times 1 equals 2. Divide by 2 both sides. And your dampening coefficient equals 1. Now, what this tells us about this system is that it is critically damped. So these are my equations over here. These ones will be used for the forced system, but this one right here is for our unforced system. This is the equation. This bottom one is the one that we will use when the system is critically damped. Now, now you have different equations for different variables of your dampening coefficient. For example, if the dampening coefficient is between 0 and 1, it is considered underdamped. And if the dampening coefficient is greater than 1, it is considered overdamped. Underdamped and overdamped, yes. So they will both have different equations to help solve for y. Alright. So we have y, and when t equals 0, y equals 0. And then we will use this equation over here. So a1 plus a2t times e to the negative t. And as we know, t is going to equal 0. So 0 equals a1 plus a2 times with 0 times e to the negative 0. Now e to anything of the 0 is actually going to equal 1, and then a2 times 0 is just going to equal 0. So 0 times 1, which leaves us with a1 equaling 0. So there is our first variable. And the second one is going to come from doing y dot. And because y dot is a form of a derivative, we will have to take the product rule of this equation to match it with the y dot formula. So when y dot equals, when t equals 0, y dot equals 3. Goes that. And then, so take that times a1 plus a2t. And then we'll take the derivative of e to the negative t. So it'll be negative e to the negative t, or minus e to the negative t. And then we will add another e to the minus t, e to the negative t. And then we will times that by at, because a1 will drop out since there's no t with it, and the t will drop out because you're taking the derivative of that, so we will just be left with at, or a2. e2. There we go. So this is your equation for y dot taking the derivative and the product rule. So we have 3 is equal to a1 plus 2 times 0. Because we have t for 0 when y dot equals 3, minus a negative 0 plus e to the negative 0 times by a. Alright, so we do know what a1 is. And then we will see from this equation here that a2 is going to be 0 as well, because you can times 0. And then minus e to the 0, and then e to the 0 is just going to be 1 again. So we have 3 is equal to 0 plus a2. And then we can see from this that a2 is going to equal 3. All right, and then we're ready to write our final equation. So y of 2, or y of t, is going to equal 0 plus 3 times by e to the negative t. So y of t is going to equal 3e to the negative t. And that is our equation, or I guess our final equation for the unforced second order system. So I will write that over here. And there's that one. So then I will erase all this. And now, another good thing, when we move on to the force system over here, a really good thing is that it does have a bunch of equations helping us solve for everything. Let me go grab my calculator quick. Because we will be needing it for the force system since it has more equations and actual numerical values to probably solve for. All right. So now we have our forced second order system. 4x double dot plus 8x dot plus 4x equals 16 times the cosine of 8t. So again, we divide that whole equation by 4. And we will get x double dot plus 2x dot plus 4x equals 4 times the cosine of 6t. And we can also find variables from this equation as well. So omega n squared is going to equal, should be 1. So omega n squared is going to equal 1 again. So that means omega n equals 1. And then we can find the damping coefficient from that. So 2 times omega n equals 2. And we know that omega n equals 1, so this means that the dampening coefficient is going to equal 1 again. Alrighty. So a couple of things we can find from this equation that is different from the unforced equation is that we can actually find something called omega naught. And omega naught is found from this side over here. And it is equals 6. And that 6 is coming from inside of this cosine times 6t. And then we can also find d naught, which is equal to 4 for this placement right here. Right. I think we got all our variables to help us solve the equation. So we will first solve for x prime. And x prime is going to be 4 divided by square root omega squared n, which happens to be 1, minus omega naught squared, which is 36, and then you square that, and then add to that the 2 times the dampening coefficient times omega naught times by omega n. Yep, omega n right there. And then we will square that 1, 2. All right. So 4 divided by square root of 1 minus 36 squared plus 2 times 1 times 6 times 1, and then square that too. And this is all under that square root. All right. We have an answer. X prime is going to be equal to 0.108. There you go. And now we can move on to phi. I think that's phi. We will now move on to phi prime, which is equal to the tangent of -1 times by the 2 times dampening coefficient omega naught omega n divided by omega n squared minus omega naught squared. All right, and we have all of these variables for that equation. So 2 times by 1 times by omega naught, which is 6, times by omega n, which is 1. And we divide that all by omega n squared, which is 1, minus omega naught squared, which is 36. And we square both of those. Oh wait, they are already squared. Never mind. There we go. So now we will do that. Tangent -1, 2 times 1 is 2, times 6 is 12, times 1 is still 12. So we will take 12 divided by 1 minus 36. And then we will take the inverse tangent of that. Equal -18.92 degrees. And then now you're wondering, is like 18.92 degrees allowed? And it is, because you think of our 4 quadrants. And I believe when it is negative, so usually it goes like this. I believe it means that it's going like this, so it's sitting down here. But it's still okay to have a negative degree. All right. So we can set up our x equation. X equals x prime, which is 0.108. And we use cosine here because, as we talked about in class, I left a blank right here because the cosine or sine that goes there all depends on this first equation that you've been given. So 0.108 times it by the cosine of 6t, and then plus 18.92 degrees. All right, and we might have to change that to radians. I believe changing something to radians is like 2 pi divided by 180 something. I think it's something like that. But anyway, I left it in degrees. So this is the equation right here for x, and then I'm also going to find the magnification of it. Just simply 1 divided by the square root. See if I have enough room here. 1 minus omega naught over omega n squared. So 6 over omega n, which is 1. Then we square that. And then we square the whole thing. And then we add that to 2 times the damping coefficient, which is 1. And then we times that by omega naught over omega n again. So omega naught over omega n. And then we square all that too. And this is all going to be under that square root. Excuse me. All right. 1 divided by the square root of 1 minus 6 divided by 1, and then you square that, and then another parenthesis and square the whole thing, and then add that to 2 times 1 times by 6 divided by 1, and then you square the whole thing again, and it's all under the square root, like I said. So the magnification is MF is equal to 0.027. All right, where'd my eraser go? Sorry, I was looking for my eraser. I think it fell. Went under here. So now we can erase all of this. And I really personally, I like the forced systems better than the unforced because I like that it kind of gives you all these equations right here and you don't have to take any derivatives. Just a little bit easier. Helps make my day. All right. So for the forced system, we have x equals 0.108 times the cosine of 6t plus 18.92 degrees. And then the magnification is equal to 0.027. Got that. And then for our unforced system, we have y of t is equal to 3e to the negative t. All right. So these are two kinds of second order systems, the unforced and the forced one. These are their two kinds of solutions. Obviously, there are much easier ones and much harder ones. I tried to give myself pretty average ones just to kind of explain what's going on with these two problems. But if you have any questions, let me know.